the discussion.
Okay.
Our next speaker. Hello. Our first speaker of this session is going to be Adrien Paquis, and he's going to talk about Omicron-X cross-correlating spectrograms to search for core collapse supernova gravitational waves.
Thanks. Hi everyone, I'm Adrien Paquis. I'm from IGC Lab Orsay in south of Paris. And actually, IGC Lab stands for Irene Joliot-Curie Laboratory. Higher. Can you hear me better? Okay. Yeah. Louder? Okay. Yeah, IGC Lab just stands for Irene Joliot-Curie Laboratory, so I'm happy to be in Maria's hometown here. I'm working with Florent Robinet in a PhD in the core collapse supernova LVK group. I'll be presenting today some work about a pipeline searching for gravitational waves, searching in gravitational waves for core collapse supernovas using cross correlation. It's called Omicron-X. And just clear outline, I'll talk a bit about the technical side of it quickly, try to be quick on that. Then talking about some maybe studies about background sensitivity, of course, and going further about the science that we want to do with SASI and neutrinos, of course, drone detections and interesting stuff like that. So first, Omicron takes its name from Omicron, which is maybe a software that you know that it produces some multi-resolution spectrograms using a Q transform. So this point, I guess I can at some point. Okay, using the quality factor Q up there, which is a fancier multi-resolution for frequency resolution, yes. And you can see that depending on the Q factor that you have a different resolution, time, and frequency-wise. If I could point, oh, okay, it's tricky. Okay, here you can see that we have a really good time resolution here, but a worse frequency one. And there we have a better frequency resolution and worse time. I like to think it as kind of viewing angles on your data. So you can imagine that we're viewing the data from different angles. So when you see one spectrogram, we actually have a couple of them behind. Of course, all the spectrograms are from O3 data, for those who you know, on the O3 burst benchmark segment. And yes. Cross-correlation. So cross-correlation, we're making some cross-correlation map quickly. Cross-correlating means that we're taking our two spectrograms. We're doing it with two spectrograms, usually LIGO, so Hanford and Livingston. And you take the two spectrograms and we're going to shift them time-wise in our case. And at some point, you'll see that the features, oh, this is really tricky. Here, for example, and they're going to align and then cross-correlate, which you'll get a big cross-correlation factor in here, which is what we're looking at. In this case, you can see that it's obviously background because it has strong delay between them of actually 2 seconds. So of course, our background will contain glitches and noise only, no gravitational waves in this case. And then what is really interesting, of course, is the zero lag when there's no time delay between them, or just a tiny few less than 12 milliseconds, the physical delay that you can have between detectors. In this case, you can see that we have these injections here. They're RadioChess 2019, I think S10 or S20 waveforms here. And they're going to cross-correlate also in this, it's really hard, in the zero time delay segment in the center. So showing that in the zero lag, we'll have some cross-correlation for our injection and hopefully for core collapse supernovas. Okay, why cross-correlation could be an interesting thing to do for core collapse supernova. It's effective to look at some patterns, especially unknown ones when we don't have models, when we don't exactly know what it should look like. And also in the way that we use cross-correlation, we don't use any SNR thresholds or any clustering. I really like the metaphor that Sergey was using of this kind of bulb of SNR that could be then, when you have a high SNR, it's sort of all located in one place, but then when it's spread out on your plane, then you have low SNR everywhere. But in our case, because we're doing the full spectrogram, it's like we're eating the full toast of jam. We're actually eating the whole jam in the end. So cross-correlation in this way is a good way to look for faint signal, especially if they have widespread morphologies like core collapse supernovas. You can see here in this example that we have some low SNR pixels. This is about SNR 7, and before we had, I think, an example with SNR 6.2. So we can go to low SNRs, of course. If it has a more spread morphology, is going to be more interesting for us. But we can go actually to some low SNRs. So for core-collapse supernova, it could be an interesting thing to do. We're producing a force reckoning statistic to decide if our event is rather likely to be signal or noise. First thing we do is define a time delay delta T max that put up simply is just the one that will maximize the cross correlation. Here in this case, it's here. Oh, I'm not good at this. And just to say that we have a precise time reconstruction for this delta T actually, which allows us to do some tests, for example, with antenna factors, some polarization, stuff like that. But in the end, we just produce this ranking statistic, R, which is summing all the bins along this line on delta T. And if, of course, if it's close to 0, means that there's no cross correlation or few, probably some noise or signal. And the other case, when it's closer to 1, we rank it as probably signal. So the whole point is getting your events closer to 1 when they're signal, closer to 0 when they're noise, obviously. I'm just finishing this. There are a lot of other technicalities which I'm not going to bore you with. But if you're interested, there's going to be a method that I published hopefully soon. And of course, come ask me if you're interested. If you have any doubts, questions, criticism, ideas, it's also the point of this, I think, conference. Please come talk to me. I'd be really happy to talk about all these details. Okay, so we're done with the technical part. Now we're looking at some background. You're looking at here about 200 years of background with the method of time shift that I think Marco has introduced. This was done on about 21 days of LIGO data, and it's about 500 million events that were processed. Just to give you a brief idea, this was done in like 8 hours with about 100 jobs that was paralleled, just by manpower of 1 person being me. So that is by pipeline setup pretty fast and I guess pretty efficient in some ways. So it's a cumulative histogram. You can see that on the left, most of our events, I'm going to try again. Okay, most of our events here are ranked on the left, and some still stick out here with a high rank values, smeared on 0 to 1. And these are going to be our problematic events, our loudest noise that we, of course, want to get kind of cut this tail right to the left to be sure that our background is only labeled as actual background. So that is kind of my fight these last month, is getting this on the more left. So yeah, let's look at these events. These are not core bounces peaks, but these are obviously some blip glitches. And they're really thin in time, they're really spread out, they're really mean, and they match really well in our case because we sum on the frequency, so that is kind of expected. You can see, yes, a couple of them, even some are multiples, but they're pretty simple to see. We've already put a lot of methods to kind of discriminate them, but we'd like to go further, especially with some machine learning that is work in progress with Marco and Yan especially, that we like to recognize and get rid of these glitches to go beyond our actual background distribution. Okay, great. Some sensitivity estimation. So we've put some injections in our data, try to find them back in the fashion that were explained in detail before. And we have some sensitivities that are comparable for two supernova models. So Orkonos 2018, MESA 20, and Pebbles S18 that are here and here. Just to give you, these are injection amplitudes, and just to give you a brief comparison with the state-of-the-art burst pipeline, CWB. We are about 2.2 times lower, or in the case of Orkonos waveform, and 4.5 times lower in the case of S18. So that is pretty, I think it is pretty encouraging for just a method that has no yet re-ranking or no machine learning inputted in yet, just for the method of cross correlation. And yes, we can see that, yes. We also have some other sensitivities here for the other waveforms. We've also done it for some just one black hole to check. And we sometimes in our data find back some black holes that were already discovered by the other pipelines before. So that is pretty encouraging that we actually are seeing gravitational waves when there are some. So yes, we are having some interesting starting sensitivity to begin with our pipeline. And we'd like to go a bit beyond on when we can do with this method actually. Okay, so that is going to be the last part. So looking at SASI and some joint search with neutrinos. I'm not going to explain you what SASI is, I think. That would be pitiful of me. There's going to be a great talk about Christina right after, about SASI detection especially. So SASI is an interesting phenomenon for us because it produces some neutrino signature, but also some gravitational wave signature that should be correlated. And so we want to exploit it for reconstruction or even maybe detection of our events. And in this regard, Omicron could be an interesting tool because it's looking at faint signals, complex signals that we don't exactly can predict with multi-resolution, of course, so different frequency bands. And we'd like to see if it's suitable to at least detect or look at some SASI signals. For that, I've tried to get as many simulations that I could. We'll build from the directories that we have access to, and sometimes asking to some of you the data. And this is just to point out that if we are looking at neutrino and gravitational waves data, it starts to get a little scarce to have a lot of events or simulations to look at. This has already been discussed about sharing method and everything, but yes, these are gravitational waves and neutrino light curves are precious for us, and we like to have, of course, more of them shared between us. If it's hopefully it's lacking and incomplete. If you have any waveform that you'd like to add or interest in that, please contact me. Yes, so what we're trying to do with intern Emile that was working with me, but also Sonia Eledri, which is working on the neutrino side at APC, was visualize these SASI events in gravitational waves and neutrinos, identifying them and probably trying to match them candidates together towards a probability, like a p-SASI, like you would have a probability of SASI. So the SASI meter was something really interesting to me from the presentation by Zidolin. And yeah, so it's more exploratory work there. I want to highlight some also, so more complete work that has been done by Alessandro Roberto, which we're excited to see develop on noise and more, hopefully some triggers from our pipelines. Okay, that is the conclusion of my talk. So I hope I convinced you that Omicron is an actual pipeline that is getting ready to hopefully detect Coco Supernova soon. It's relying more on cross-correlation in its score. Its sensitivity is getting closer and closer to the actual state-of-the-art sensitivities. It's meant to evolve, of course, to have some new features, so test some new techniques. And I want to mention that it's really easy and light to run. If you're interested in maybe looking at some triggers, trying to run it for yourself, that is something that you can easily do. You just need one. Well, I mean, it's quite easy to run. I've helped some interns also run it, so please give it a go if you want to. And yes, for estimating sensitivity to SASI, we still need more waveforms and probably better sharing method has already been discussed. The next step that I'm excited about is machine learning glitch detection, of course. I want to test SASI detectable unit. I'm curious also about the joint analysis with neutrino triggers that we're working with Sonia. I'd like to maybe think of how to say ways to have both gravitational waves and neutrino data that we could try to look at some joint searches on. Sorry. There's also the idea of having a targeted mode, especially to look at some targets like the one that Rosa showed, for example, 2020 IXF. And in the last part, I think about detection is more on the G modes and F modes, high feature frequency, that I'm interested in for the detection part. Maybe that's something that I'd like to constrain on and put on some modeling and stuff like that within the pipeline itself. So getting more and more in the Coco Supernova light model search. Okay, thank you for attention.
Thank you for the talk. Are there any questions?
Hi, Adrien. Thank you very much for the nice talk. I just have a question about slide, I think 13 or 14, where you were showing like the detection efficiency curves. Yeah, so I was just curious, do you know what the distances of these look like, let's say at like 0.5 detection efficiency? Like just sort of what are the reach of each of these models?
These to get an idea of this, I think we can take the CWB reach and I think divided by the square of these sensitivities, so probably divided by 4 or 10. So in the reach, so we're a bit behind. So I think I don't want to give wrong numbers for the CWB search. I've been looking more at the benchmark, but I realized that not something, an internal node that I can give out. But just so you have an idea, we're a bit behind, of course.
Okay, good to know. Thank you.
About let's say about a factor 10, I think, in distance, to be conservative. And this is, of course, on all three runs.
Thank you very much for the very interesting and relevant subject. We hadn't discussed much yet about that. My question, I have two questions. The first is, how frequent are those glitches? I have no idea whether you get them every minute or whether you get them every hour, or what is the rapid time typical for a rate?
Again, I think it's more about the, I don't want to say that some right answer, because I look at like 200 years of data. So in the end, I don't really know how much are there, but it's quite frequent. I think about the order of maybe an hour, 20 minutes, some stuff like that, glitches. If someone can back me up. More than that? Oh, wow, okay. Yes.
Yeah, sure.
Oh, you're talking about all the glitches in general, or just the blip?
Let's say we had, well, this is now very difficult to define, but let's say we had a 10 kiloparsec supernova, 10 kiloparsec distance, and we had an average type 1 rotational core-bound signal from the Dimmelmeier. Do you know how much endangered the detection of that would be by glitches?
I don't think we would be in danger, because I don't think you would see only the core bounce. I think you'd see the core bounce and the high frequency mode. So
well,
if you could really only detect.
I don't think we are endangered if you think of neutrinos, which we will detect. But in the worst case, you could think of a very much suppressed neutrino signal, where you don't get this prompt nu-E burst because of neutrino flavor conversions with a certain mass hierarchy. You can make this spike go away. The spike anyway is electron neutrino, so whether we measure the spike or not is also a bit ambiguous. But the spike might not be there if we are very unfortunate with the flavor hierarchy, with the mass hierarchy, sorry. But then we only have the core bound signal from the gravitational wave side. So I would just like to know whether we are in danger detecting the core bound signal if there were rotation, significant rotation at a 10 kiloparsec distance supernova.
So we're good at, if you have a gravitational wave signal and it's basically just one spike, we're quite good at detecting those with CWB. But also the false alarm rate will be higher because there's a larger number of glitches in the data that are just one spike than there is long duration glitches. You'd also have a problem that it's harder to say it's a supernova. So if you have like a lower frequency one spike signal, everyone will assume that it's a high mass binary black hole. And if it's like higher frequency, it's like go nuts with whatever your favorite astrophysical source is. There's loads of them. That's just one spike. So you have danger from the glitches, and you have danger both of confusion with other astrophysical sources. But the lower in signal to noise ratio you go, the more of these glitches there is. So if you have like a really loud 5 sigma event, it's not going to get confused with glitches. If you have a lower signal to noise ratio detection, then we would be less confident that it's real because it could be one of these glitches.
I understand that part, but on the other side, again, apologies for my ignorance, when you say other astrophysical signals, I mean, we have a good chance in our galaxy to know that there was a supernova in that time window, which is then relevant. Maybe if you think of the delay for shock breakout and supernova observation, a couple of days. Are you afraid that there is other sources we might see in that time?
I mean, if you get the core bounce signal and it's exactly the same time as the neutrino signal in the exact sky position where we observe the supernova with your eyeballs, then I think that we would all pretty be sure that it is. But you know, there's still going to be like one person that's like, but what if it's a coincidence and it's a binary black hole?
Sure, that is. And my second question is on your summary slide. Could you show that again?
Yep.
There was a sentence which was interesting, and I would like to go into a bit more specifics on that. Estimating sensitivity to SASI needs more waveforms and better sharing methods. So first, why more waveforms? I would suspect that the SASI signature is pretty simple because of its quasi-periodicity, and I think the 20 or 30 signals you have out there on your list of models are already sufficient to cover the current possibilities in models. That's what at least would be my feeling. And the second part, what is better sharing methods?
Oh, that's better sharing. I don't think I'm the one to say that. I just wanted to highlight to a point of, even when we're looking at detection for a PhD, it still has some impact on how we work. But for why we would need some more waveforms, we don't have so many that have actual neutrinos and gravitational waves at the same time.
That's
And
true. Yeah.
and but also because we're not, especially if I'm thinking of machine learning or other techniques, I don't want to train on one simple model, but maybe have some couple of them. And if you look in details, sadly I just have one here, but these SASI models look really different. These sometimes you have they can be really long, sometimes they're really and they're also from different waveforms, of course, parameter space. So I don't know all the theory that is behind, but what I see in the waveform, of course, that they're pretty different, and I wouldn't want to just train on a couple of them and in the end be constrained. It's still in the large sense an on-model search, and I don't want maybe to get too much in a zone. And about the false alarm rate stuff, how dangerous it is to detect these glitches. I think it depends on the false alarm rate you're giving yourself to. Here, it's 1 per 10 year. We've been looking at some false alarm rates of like 1 per 10 year, 1 per year, sorry. And then you see more glitches, but you see also more events. And that I think is a balance that that has been already discussed on. Do we want the 5 sigma? Do we want a false alarm rate for 1 per century, 1 per day? I think it depends on if we have neutrino, if we have electromagnetic counterpart, stuff like that. That will be that if we have a detection or an event should be discussed together.
Adrien, thank you for the beautiful presentation. I also want to compliment you, as Tomas did indirectly, on the extensive set of waveforms that you have used in this study. The reason I want to compliment you and also point that out is, as I said the other day, all models are important and useful, but not all models are created equal. Mm-hmm. And that's a fact of life. And when analyses are done with a small group of models, say from a particular group or maybe 1 or 2 groups, those models will be biased. And so, you know, we've seen a mix of that. And I highly recommend people follow your good example here. I wanted to ask you something. I don't expect you to remember all the details of all of your models, but I wanted to ask you if there was anything. Did anything strike you as different or peculiar about our 9.6 model?
With what, sorry?
Did anything strike you as unusual or particular? Did anything jump out at you, as it were, with regard to the Metzger 2023 9? You listed it as D9, but it's D9.6? Yeah. Not that you would remember, but
I think looking at those, because I've also been citing some of them, not exactly those. I think there were some features also on the sides and some glitches that we had to cut sometimes. Having some filters, and that is also some nasty stuff that, as someone that is not an expert, I had then to get back to some experts and stuff like that. And it's a forth and back that is, I think, a pity that the one person should do itself and maybe have a collective effort sharing information or the waveforms like that.
No, I'm just bringing that up because as I'll discuss tomorrow for reasons that'll be clear tomorrow, that model, the gravitational wave emission from that model is different than anything else. Okay. And there's a reason for that, which I'll discuss tomorrow. And, you know, that's why I was wondering if in your analysis, if that one jumped out in any particular way.
There's the sensitivity here. I can look at that in details.
Yeah, maybe we can talk offline.
Of course.
And I can show you what I mean. And then tomorrow we'll discuss it more.
Sure. Okay. There's a question by Jade.
If you need some neutrino signals to go with your gravitational wave signals, I'm sure most people will be happy to give them to you if you send them an email, or if they're scary, you can email me and I can email them for you.
Yeah, I have actually done on that already, either emailing you or people. So it's just when you have like 20, 40 waveforms to look at, it takes time, of course, and sometimes you're just limited by that too.
It's easier if you go with recent ones as well, because
Yeah.
after a while, people move their data from their simulations into some storage, and then if they have to calculate something new, they have to get it back again, and that's a bit of a pain.
It's a complex question, I think.
Is there any last quick question? Then let's thank the speaker again.